Primary progressive aphasias are really a family of disorders, and they give us the opportunity actually to make very early diagnosis of these neurodegenerative disorders.
Magnetic fields generated by the human brain are really tiny. They're about 7 orders of magnitude smaller than the Earth's magnetic field. Superconducting detectors are sensitive instruments that can measure very tiny magnetic fields.
The rhythmic oscillations in the brain are conventionally studied within specific frequency bands, ranging from low frequency to high frequency. In this study, we specifically examined the delta theta band to 8 Hz band and alpha band 8 to 12 Hz and beta band, which is from 12 to 30 Hz.
And when we put a human in this detector, we can detect magnetic fields generated by the human brain. And then we have algorithms that enable us to take these sort of measurements, sensor measurements, and reconstruct exactly where these magnetic fields are coming from in the brain.
The oscillated rhythms in the brain are a fundamental property of cortical networks. They represent the coordinated activity of neuronal firing in the brain. We examine the resting brain rhythms in patients with primary progressive aphasia variants.
So here at UCSF, we conduct a lot of research in individuals with primary progressive aphasia, also called PPA. People come from all over the country because we are one of the main centers that study these rare neurodegenerative disorder. We, in collaborations with other clinicians and researchers around the world, have come up with a classification of the disorder that was once thought to be unitary. So there was one primary progressive aphasia. We now know that there are 3 main types that really affect different networks of the brain and so present differently. And these new techniques can really give us the opportunity of not only looking at which networks are involved in each of these variants of PPA, but really understand how the mechanism at the network level and the electrical and magnetic level, what is going on and how these neurodegeneration affect cognition.
And we can reconstruct not only which brain regions are active and contribute to measurements that we make outside the brain, but also the network of brain regions and how they coordinate their activity.
We examine the global functional connectivity of the resting brains in the 3 PPA variants: the logopenic variant, the semantic variant, and the non-fluent variant. We found that within alpha and beta bands, PPA patients show consistently reduced functional connectivity patterns. Furthermore, the spatial distribution of these functional deficits involved distinct brain regions in each PPA variant. Within alpha band, the patients with logopenic variant showed reduced functional connectivity over the left posterior temporal regions of the brain, whereas the patients with non-fluent variant showed reduced functional connectivity within the left inferior frontal regions of the brain. The semantic variant patients showed the most significant deficits over the left temporoparietal junction. In contrast to alpha and beta bands, the low-frequency delta theta band showed significantly increased synchrony in patients with logopenic variant. We demonstrated distinct spatiotemporal patterns with network-specific hyposynchrony of alpha and beta bands in each PPA subgroup.
The results of the study are very exciting because, firstly, it demonstrates a proof of principle that this form of functional brain imaging can really shed valuable insights into the biology of variants on primary progressive aphasia. So it helps us understand the diseases a bit better, and better understanding hopefully will lead to better therapy, better tracking of the diseases as they progress, and as new therapies come, we can monitor the effectiveness of these therapies using this imaging modality.